2 kilogram block starts from rest at the top of a frictionless incline that is 5 meters long and inclined at 30 degrees above the horizontal. At the bottom of the incline, the block compresses a horizontal spring with a spring constant of 400 newtons per meter. Neglect friction throughout the motion and assume that g, the gravitational acceleration, is 9.8 meters per second squared. Determine the maximum compression of the spring. So this is a diagram of basically what it would look like. And here we have the block and it's sliding down to hit this spring. So we can start, let's draw the forces. And the forces acting on the block are the force of gravity and the normal force. Now, at first glance, we might think to use Newton's laws on this problem, because after all here, for the first part, the block is just sliding down an incline, and that's something that you can derive the acceleration for and has a constant acceleration. However, in the second part, it tells us to determine the maximum compression of the spring. And while the spring is being compressed, it exerts a variable force on this block, which means that the acceleration on the block will also be variable, and hence we cannot use the constant acceleration kinematic equations to find the maximum compression. So instead we must use a different method, and here it happens that if we choose the block, spring, and the earth as a system, then the total mechanical energy will be conserved because there are no non-conservative or frictional forces acting upon the system. So initially, all of the energy is stored as the gravitational potential energy of the block. And in the end, when it slides down and compresses the spring, all of that gravitational potential energy will be transferred into the potential energy of the spring. So we can write out the equation of energy conservation. So the initial energy in the system is going to be equal to the final energy in the system. So the initial energy is just simply the gravitational potential energy of the block initially, relative to the bottom of the incline where it will be at the end. And it doesn't have any kinetic energy or other potential energies in there. And then at the end, it loses all of its gravitational potential energy, and that gets transferred into the potential energy of the spring. So this is our equation for the conservation of energy. And then we can further write this out. So the gravitational potential energy is just the block's mass times the gravitational acceleration g times the height. And in this case, the height is this represented by this, if we can draw. So this here is the height. It is the change in the height that the block undergoes as it slides down from the incline to the spring. And we are given that the length of this part of the incline is 5 meters long. So the incline is 5 meters long, meaning that this part along the incline is 5 meters long. However, the length of the incline is not the same as the height h. Instead, we can use trigonometry to figure out what h is. So if this is the angle theta, then we have that the sine of theta is equal to the opposite over the hypotenuse. So from this, we have that the height is going to be equal to the length of the incline times the sine of the angle. Also, it might be a little unclear here, but essentially this would still be theta. And this was only because I drew this spring a little higher. If we were to remove this, it would actually look like this. And instead, this whole length is the height. And this whole length is 5 meters. And instead, the spring is like down here. So this might be a little more clear why we can do this. And so now we have the gravitational potential energy, and the final energy is stored in the potential energy of the spring, which is given by 1/2 times the spring constant times the distance compressed squared. So now all we need to do is rearrange and solve for x. So first, let's do kx. Let's multiply both sides by 2. So 2 on this side and 2 on this side. So we have kx squared is equal to 2mgh. And then we can divide both sides by k. So x squared equals 2mgh over k. And finally, we can square root both sides to get that compressed distance x is equal to the square root of 2mgh over k. And now let's plug in L sine theta into this height h here. So this becomes 2mg L sine theta divided by k. And so now we just need to plug in everything from the problem. So we're given that L equals 5 meters, M equals 2 kilograms, K is 400 newtons per meter, theta is 30 degrees, and G is 9.8 meters per second squared. So now all we need to do is just plug these numbers in. So if we do that, M is 2, G is 9.8, L is 5. We're running out of space here. This is sine 30 divided by 400 newtons per meter. And then if you plug this into a calculator, you should get that the maximum compressed distance is about 0.495 meters. And that is the solution to this problem here.